This recording is protected by copyright. No part may be reproduced without the prior permission of the University of South Australia.
Yes. Let me give you a brief justification for that formula. Okay? No, it's not a proof, it's just an idea. Let's say that your function f is 2x plus 3. So the derivative is 2. It's a straight line. The derivative is always 2. Okay? And let's say that g is 4x plus 1. The derivative here is always 4. What happens if you do f composed with g? Okay? Now, the formula, this is going to be my first input. So start with x. Yeah, I want to do g composed with f. Excuse me. So this is going to be my first input. And then I take that into the other one. That's what's going on. Okay, I'm going to use this as the input for the other. So that one I'm going to call w. And w goes to 4w plus 1. Okay? And what the formula says is that dy dx is dy dw times dw dx. So you notice that what the formula says is that they should multiply each other. Okay? Why multiply? Why not add? Why not divide? Why multiply? Well, take a look. I can do this one by hand. This one is 4 times 2x plus 12 plus 1. And this is a straight line. What's the derivative of a straight line? What's the slope of a straight line? It's 4 times 2. They multiplied, right? One of them was 4, the other was 2, and they came out. Forgot my water bottle, I'm sorry. And they came out as 4 times 2. That's why in this formula you multiply instead of add or divide or whatever you do. Okay. There is another explanation in terms of physics, but we'll postpone that for when we talk about derivatives and physics. Okay? Of course, there is also an explanation based on mathematical proof. We're not going to do that. Right? But I hope this one example here is a good indication of why they multiply instead of anything else. Okay. This is a topic I really enjoy, implicit differentiation, and it is a somewhat short topic. Remember when we started, we said, hey, x squared plus y squared equal to 1. This is a circle. This is the equation of a circle. The center of a circle is the origin 0, 0, and the radius is 1. Okay? So in the picture, there you go. Kind of, yeah. Pretend this is the center and pretend the radius is constant equal to 1. Now, that is fine in terms of geometry, but it's not a function. Okay? It simply is not a function. So in principle, I cannot use the rules of derivative to find anything about this. Unless, say for instance, I want to find this slope here, the slope of a tangent line, and perhaps even the equation for the tangent line on the circle. I can't. It's not a function. You see, one way around it is solving for y in terms of x. If you solve for y in terms of x, and now you take a square root, there are two possibilities here. Either you're going to have to choose a plus or a negative square root of 1 minus x squared, right? Which one is it, the plus or the negative? Well, in my picture, I wanted the top bit, so it's going to be the plus. If I wanted the slope on the negative bit, I would take the minus. Yeah? Comments? Complaints? No? So if I want to do it, for that picture there, if I want to find slopes, I would use this one and take derivatives here. And how do I take a derivative of this? Using the chain rule. Okay? That's what I would do. It turns out that there is an alternative to it. Okay? There is another way of finding the derivative, dy dx, the slope, without having to solve for y. And it goes like this. And that's the whole point of this topic, implicit differentiation. You want to find dy dx, but you don't want to solve for y to do that. Right? Go back to the original equation, x squared plus, plus y squared equal to 1. Okay? I am going to do this. I am going to pretend that both x and y are functions of another variable that is not in this problem. Call that variable t, if you will. You can call it whatever you want, but okay? And I'm going to take a derivative with respect to the new variable t that's not in this problem. Okay? So in fact, this equation here, you want to think of it in this way. But George, there isn't a variable there. Never mind. Never mind. Just pretend that there is. Okay? What's x of t? You give me an input t, and it gives me a number for x. That's all. And you give me an input t, and it gives me a number for y. That's all. And these numbers, turns out that if you square one, square the other, and add, you get 1. If you want to think about this in terms of physics, maybe what you do have is that t is time, okay, and you have an insect walking on top of a circle, and it's moving over the circle. Maybe it's coming back, maybe it's going faster and then coming back, and maybe just, okay? And the position of the insect is x of t, y of t. It's the position of x position on time t and the y position on time t. As time passes, it moves along, okay? So now take a derivative. Take a derivative here. On the right side, the derivative of 1 is the derivative of a constant. It's 0. On the left side, all right, what is the derivative of x squared? Well, using the chain rule, it is 2 times x times dx dt. I'll get to it in a moment, okay? Plus, what's the derivative of that? It's 2 times y times dy dt. Okay? If this step here is unclear because you don't see that the derivative of this quantity is that quantity. Hold on for a moment. Let me just finish here, and then I'll go back to this. Okay? There you go. Now you need to simplify this expression. I'm going to divide everything by dx dt. This step is always done. This is what you do now. Divide by this. You get 2x plus 2y dy dt dx dt equals 0. Cancel the dt's. You get dy dx. Now solve for dy dx. Dy dx is the derivative, right? Solve for this. 2y dy dx is equal to negative 2x. Divide by 2y. Because the 2's cancel. And that's it. Okay? So let's see how to use that. Again, I'll bring you back to a few lectures ago when we started talking about calculus. One of the great advantages that calculus gives you is that you can start doing geometry and all that stuff without drawing a single picture. That's an advantage. But one of the disadvantages is that you can do geometry and everything without drawing a single picture. Okay? So go back to the picture. Let's take a point on the circle here. Okay? So I need a value for x and a value for y, and I need them to be like this. Okay? So give me a value for x. A quarter. No, a half. Okay? Let's take x equal a half. Right? So if I square that, that is 1/4. So y squared is 1 minus a quarter is 3/4, right? So I'm going to take for y the value cube root of 3 divided by 2. So if you square this and you square that, they add up to 1. Okay? Where is this? Well, x is 1/2, so it's here. And y is square root of 3 on 2, which is that height over there. What's the slope of a tangent line that you can draw here? This formula here is telling what the slope is. It's negative 1/2 square root of 3 divided by 2. So it's negative 1 on square root of 3. You can tell it's negative because it's sloping down. The precise value, negative 1 on root 3, you get in the calculator. Okay? So let's see. Waiting for you to finish copying. I'm going to get rid of that bit. Let's see why this bit here is true. Okay? T xt xt squared. So I'm going to call this W. This is W squared. So if you want to take the derivative of x squared, if you want to take the t derivative of this, it is going to be let me call this thing something like y, right? So if you want to take a t derivative of y, it's going to be dy dw multiplied by dw dt. Y is w squared, so dy dw is, what's the derivative of w squared? 2w multiplied by dw dt. I cannot do that derivative because I don't have, w is just x, so this is dx dt. W is just x. W is equal to x. So this is 2x dx dt, which is what I had here. Okay? Let's do a few more. I'll go there. Okay, let's see. I'm just going to write an expression, not a very hard expression, involving x and y. Okay? Y squared plus y plus xy is equal to x squared plus 3. Okay? Now, you notice the following. When I had x squared plus y squared equal 1, I could solve for y in terms of x. There was a square root in there and stuff. Here, it's harder to solve for y in terms of x. I'm not saying it's impossible, but I'm saying it's harder. You may not even want to try. Okay? But it is still possible to find dy dx. Okay? So let's see. What's the derivative of y squared? With respect to t. That's the problem, right? We are doing a derivative, not just, it's not the derivative of y squared with respect to y. It's the derivative of y squared with respect to this mystery variable t that's not there, not even showing there, okay? So if you want, this is this. That's the chain rule. This one here just told me how much it is. It's 2y. And then you leave dy dt there, because you have no way of knowing who that guy is. Plus, the derivative of y with respect to t is just dy dt. You don't need the chain rule here. Plus, now, in here I have x times y. There's a product here. So you need to use the product rule. The derivative of the first, so this is dx dt times y plus x times dy dt. I use the product rule here. Equal. What's the derivative of x squared? 2x, right? But remember, it's a t derivative, so it's multiplied by dx dt. And the derivative of 3 is 0. So you don't write anything anymore. Okay. Let's do it slightly differently from what I did before. Multiply everything by dt. Okay? Multiply everything by dt. 2y dy dt. If I multiply by dt, the dt cancel. Dy dt, if I multiply by dt, the dt cancels. In fact, you notice that the value dt cancels from the denominator everywhere. So I'm just going to write the same formula, but without the dt. Okay? I'm going to write 2y dy plus dy plus dx times y plus x times dy is equal to 2x dx. And now divide everything by dx. Two y dy dx plus dy dx plus y plus x dy dx is equal to 2x. Multiply by dt. Divide by dx. The bottom formula down there, solve for dy dx. Everything that has a dy dx, you put it on the left. Everything that doesn't have a dy dx, you put it on the right. Okay? So 2y dy dx plus, that's this term here, dy dx, that's this term here. This doesn't have a dy dx, I'll move it to the other side. This one I'll leave, plus x dy dx is equal to 2x minus y factor the dy dx, and I'll divide by that quantity to find that dy on dx is 2x minus y, 2y plus 1 plus x. Now, if you are like me, when I learned this thing quite some time ago, oh, you know, you lost track of what you're doing a long time ago. You're just following the rules. You're just going through the motions, okay? It's unavoidable. It really is unavoidable. Problems on implicit differentiation, they are problems where you have to really come to terms with the fact that you're going to be doing the calculation after calculation after calculation, one after the other, because that's all there is to these problems. Okay? Why is that? Because, look, if it were easy to solve for y at the beginning, you would have done so. Okay? If you could solve for y in terms of x, then you would take the derivative using the rules in here. But it's not easy to solve for y in terms of x. So you have to go this path. There's nothing you can do but follow a path like that. So let's see. Let's see. If I erase and you are copying, you have to tell me before I erase, okay? It's a telltale sign when I get the eraser. And you go, oh, is he going to erase that, or he's just playing with it? No, I'm going to erase that. Okay, let's see. If you are doing implicit differentiation and you see a term like this, how do you take a derivative of that? That's what happens. Okay? If you are doing implicit differentiation and you see a term like this, what do you see here? 3y squared dy dt. If you're doing implicit differentiation and you see this, what do you see there? Yeah, it should be 1, but you have always to put a dx dt. Okay? If you're doing implicit differentiation and you see a term like that, there's a product here. You have to use the product rule. So it's more complicated than that, but you get the idea. Each one of them will have a ddt in it. So it is dx dt times y plus x times dy dt. If you're doing implicit differentiation and you see a term like this, just the y is squared, not the x. Okay? It is dx dt times y squared plus x times the derivative of that, which will give you 2y dy dt. See if you agree with that. If you're doing implicit differentiation and you see something like that, you're going to use the quotient rule. Okay? this table here should carry you a long way when you do implicit differentiation. A really, really long way. Yeah?
Can you do implicit differentiation without including t?
Ah. Now here's the little secret for today's class. You can do it either with a t or without a t. Okay?
Because I got taught to do it without t.
Yeah. If you do it with the t, you can get rid of a t very easily by doing this trick. Multiply everything by dt, and the t goes away. And that is probably how you learn.
Yeah.
There's a big advantage to doing that with the t when you do the topic that we're going to do next, maybe not next week, but the one after, called related rates. Okay? So of the two ways of doing it, I do it with, because it will help us later. I don't think the book does it with. It does differently. Okay? Check it out. In the end, you land on the same spot. Okay? You will land on the same spot. If you just multiply by dt, you fall into the stuff that the book does. Now, practice exercises on that, okay? Last topic. For today, is the sign of a derivative. And it's a completely different topic. Okay? So you have a function and you took a derivative. We already said something about what happens when you set that equal to 0. Okay? Setting the derivative equal to 0 and solving it tells you the values of x that could be a local maximum or a local minimum, or maybe both. Okay? I'm going to draw the following here. This is the value x equals 0. And this is the value of the derivative. The derivative is 0 here. Okay? Now, are there any other values of x for which the derivative is 0 in this case? Are there any other x's that will make the derivative 0? Yes, you do know. X equal 1, 2, 3, 4, 5. I mean, which values of x make this equal to 0? There's only one value. Plugging in x equals 0 here, right? So no other value of x will make this 0. Okay? Now let me ask you this question. Can the derivative be positive here and negative here? In principle, yes. Right? So it's positive here, it's negative here. Now move these points closer together. When the positive meets the negative, what has to happen there? It has to be 0. It's the only thing between positive and negative is 0, right? Okay? If the function is continuous, but this function here is continuous. And I know that there's no 0 here, because this is the only one. So this cannot be positive and negative. Okay? It either has to be all positive or all negative. Okay? Well, what is it? Is it positive or negative? Plug in a value of x and find out. This is x equals 0. plug in x equal 2. If I plug in x equal 2, what do I get? 4. 4 is positive or negative? Positive. So everybody here is positive. And everybody here, you can check, is negative. Okay? Now think in terms of a graph, in terms of slope. Positive slope means that the graph is doing what? It's going up or down? Up. Okay? Zero slope means the graph is horizontal, exactly horizontal. And negative slope means that the graph is moving down. So take a look. Negative slope, the graph is moving down. Horizontal, moving up. So the graph of this function here looks like this. Down, 0, up. Horizontal, up. It's the graph of a parabola, right? You can do a better looking graph, but it's going to be like that. Okay? So remember, the sign of a derivative, if it's positive, it means it's sloping up. As you move from left to right, it's sloping up. If it's negative, it's sloping down. Okay? I know I'm going to regret this, but anyway, let's go for it. Okay? So let's see. What's a derivative? Well, you can multiply this through. So let's multiply it through. So this is x cubed. Now it is 3 plus 1, 4 minus 2, 2 plus 2x squared. Now let's see, this is x. Negative 2 plus 3 is 1. Minus 6 is negative 5. 6. I hope I didn't make a mistake. Check my work, please. That's the derivative. Okay. So I want to equal this thing to 0 and see what happens. Did I get this right? Is this right? Yeah? Yeah. Okay, so let's see. X is equal to negative 4 plus or minus the square root of 16 plus 4 times 5 is 20. 20 times 3 is 60 divided by 6. So this is negative 4 plus or minus the square root of 76 divided by 6. Oh, fantastic, fantastic. Oh, now let's see. 16 is 4 times 4. And 60 is 4 times 15. So this is negative 2 plus or minus square root of 19 divided by 3. All right. I said I was going to regret it because I knew these numbers are not going to come out very well. Okay? So let's see. Question for you before we go on. Are you extremely confident of this formula here? It's the formula to solve equations of degree 2. Yeah, it is the formula that says negative b plus or minus the square root b squared minus 4ac divided by 2a. Remember that? X is equal to this, and it's ax squared plus bx plus c equals 0. It's any formula that's over 3,000 years old, you respect, right? So there. So let's take a look. Let's take a look at what happens here. I'm going to put these two values of x in here. One is negative 2 minus root 19 divided by 3, and the other is negative 2 plus root 19 divided by 3. Here. Okay. Somewhere in between is 0. Okay. For these two values of x, the derivative is equal to 0. That's how I found these guys. So I know the derivative is 0 here and 0 here. This is the formula for the derivative. Is that formula continuous? Yes, because it's a polynomial. That means that in between, everybody has the same value for the derivative. Okay? Positive or negative, I mean. The same sign. So between this value of x and that value of x, either the derivative is positive in between or negative in between. It cannot change, because if it did change, it would have another 0 in between, and we know there are none. Okay? Which one is it, positive or negative? Well, here, find a number x between these, an easy one. This number is negative, this number is positive. So x equals 0 is in between, right? Plug it in here. 3 times 0. Negative 5, maybe. Which one? This? No, if you plug in x equals 0, 3 times 0 plus 4 times 0 minus 5. I think you plugged in another value. You plugged in, I don't know. Which value did you plug in? 0. No, this gives you 0 plus 0 minus 5. It gives you negative 5. Okay? But in any case, it does give you negative. Now, don't make a mistake that is common, okay? Saying, oh, this is negative, this is 0, that's got to be positive. You have to check. It's not hard to check. Pick a value of x that's bigger than this. Give me a value of x bigger than that. How about 50? Is 50 big enough? Or 100? That's bigger, right? If I put 100 here for x, this is going to be positive, right? Do you have any questions about that? No. So it's positive here. Now you have to pick a value of x that's negative, but below that. How about negative 4? I'm sure negative 4 is below that. Okay, I'm dividing by 3. I'm got to be. If I put negative 4 3 times, negative 4 squared, negative 4 squared is 16. 3 times 16 minus 16 plus, or negative minus 5, that's going to be positive. Okay? If you have a calculator, it will give you the answer very easily. So look at what I'm seeing here. I'm seeing positive, negative, positive. So it looks like this function here has a graph that does this. Positive, so it grows. And then hits this value of x here, becomes negative, so it decreases. And then it hits that value here, and it grows forever again. So it's looking like that. And if you plot it, you're going to see that is exactly like this. These three values here are -3, -1, and 2. From the way I picked it. So the moral of the story, because this one story has a moral, is when you take a derivative and make it equal to 0, and we said, oh, these could be max, could be min, right? Now you have a way to tell. There are two values of x here, this one and this one. Let's take a look at this. It's this value of x. In my picture, it's this value of x. Before it, the derivative is positive, so it's increasing before it, and it's decreasing after it. Now picture it in your mind. Increasing before it, 0, peaked, decreasing after. So that's the max. It increases to it and decreases after it. That has to be a local max. So now you know that this is a local max. And you can see it in the picture. Look at the next one. It's decreasing before it. It's dipping towards it, reaches the point, and then it increases after it. That's a local min. They could be global, but you don't know. All you can say is local. Okay? In this case here, they are not local or global. They're not global. They are not the absolute max or the absolute min. You can see from the picture that it keeps going up and down. Okay? But they are local. All right. If you had a picture like this, let's see all pictures you can have. All pictures you can have. Plus minus. This is a max or min? Yeah. Max. Local, always local, but max or min. Look, increase, decrease. So max. Decrease, increase. What do you think? Min. Up and up. Can you have up and up? Yes, you can. It's not a max, it's not a min, it's neither. Okay, here's a picture. That's something that goes up, stops to breathe, and goes up again. Okay? That's called an inflection point. There's a name for everything. If you're climbing a mountain, you really like those. It gives you a rest. And the last picture, which is just like that picture, but reversed. It's also an inflection point. So these are the 4 possibilities. There are no other possibilities, and they tell you everything you need to know. Oh, thank you very much. I'll see you on Thursday for another exciting tutorial.